Megaprojects stand as the most ambitious and awe-inspiring expressions of engineering on the planet. These massive undertakings costing billions, spanning decades and involving tens of thousands of people, reshape landscapes, economies, and societies. Today, this exploration embarks on a comprehensive journey through the world's largest megaprojects, revealing the scale, complexity, and ingenuity required to design and build these colossal feats. At their core, megaprojects are defined not just by size, but by the magnitude of challenges they pose. Whether constructing bullet trains spanning hundreds of miles, erecting skyscrapers that defy gravity and time, or engineering dams that alter rivers and power nations, these projects push human capability to its limits. They embody a convergence of disciplines: civil, structural, mechanical, electrical, environmental, and more, intertwined with economics, logistics, governance, and risk management on unprecedented scales. The headlines capture the scale: megaprojects with budgets exceeding tens or hundreds of billions of dollars, engaging engineers, architects, planners, governments, and contractors across borders. But beneath the surface lies a layer of staggering complexity. Unforeseen geological conditions, political shifts, environmental protests, and technological challenges demand adaptive strategies and resilience. One wrong calculation or delayed delivery can cascade into massive cost overruns and years of delay. Consider the engineering marvel of the Three Gorges Dam in China, the world's largest hydroelectric power station. Stretching over 2 kilometers across the Yangtze River and standing 185 meters tall, it balances power generation for millions with flood control and navigation enhancements. Designing and constructing this project required managing unpredictable river flows, relocating 1.3 million residents, and conserving rich ecological habitats. Multiple dams and powerhouses, complex spillways, and giant ship locks integrated into a single cohesive system illustrate the extraordinary multidisciplinary collaboration involved. Similarly, the sprawling International Space Station represents a different class of megaproject, an orbiting laboratory resulting from decades of international cooperation among NASA, Roscosmos, ESA, JAXA, and CSA, assembling hundreds of modules and systems in zero gravity through hundreds of spacewalks push the limits not only of engineering precision, but of logistics, safety, and diplomacy. Operating this one-of-a-kind facility challenges engineers daily to maintain life support, power, and communications from hundreds of kilometers above Earth. Megaprojects reshape urban skylines dramatically. The Burj Khalifa in Dubai, towering at 828 meters, exemplifies cutting-edge structural engineering. The building's tapered design counters wind vortex effects, while the foundation rests on deep piles penetrating the desert sands. Innovative materials and construction methods allowed work to proceed in extreme heat. The tower incorporates complex sustainable systems for water reuse, cooling, and efficient vertical transportation, managing thousands of occupants daily. Transportation megaprojects drive connectivity on a continental scale. The Channel Tunnel linking the United Kingdom and France, or Crossrail beneath London, involves tunneling through variable geology at significant depths with high-speed rail integration. Megaproject engineers navigate geological faults, groundwater inflows, and urban infrastructure congestion. Managing logistics with thousands of workers and minimizing impact on surrounding communities requires advanced planning and stakeholder engagement. Energy infrastructure megaprojects power entire countries or regions. Nuclear power plants like the Kashiwazaki Karawa plant in Japan or new modular reactors in development define the apex of safety, reliability, and regulatory scrutiny in engineering. These projects demand intricate thermal hydraulics analyses, radiation shielding, structural integrity under extreme seismic conditions, and exhausting quality assurance. The social and political dimensions of megaprojects cannot be overstated. Conflicting objectives among governments, investors, environmental groups, indigenous communities, and general public necessitate transparent governance, participatory planning, and dispute resolution mechanisms. Projects span decades and multiple political cycles, requiring institutional frameworks to maintain continuity and accountability. Digital tools have transformed megaproject management. Building information modeling. BIM integrates 3D models with scheduling, cost, and resource data for real-time decision-making. Sensor networks enable live monitoring of structural health, excavation progress, and environmental parameters. Artificial intelligence assists in logistics optimization and risk identification, although human expertise remains paramount. Risk management in megaprojects is uniquely intricate. Uncertainties in geological surveys, price fluctuations in materials, labor disputes, and regulatory changes fuel the potential for cost overruns. Studies indicate many megaprojects exceed budget by over 20%. Contingency planning, contract structuring, and adaptive project controls mitigate these inherent dangers. In this series, we will dissect these colossal endeavors not merely by their size, but by the ingenuity, challenges, and solutions they embody. Each part will delve into different domains: megabridges, tunnels, skyscrapers, energy systems, transportation networks, water infrastructure, and aerospace megaprojects, revealing the deep engineering principles and human stories underpinning them. Prepare to immerse yourself in the feats reshaping our physical world, where ambition meets precision, where innovation wrestles with complexity, and where engineering transcends ordinary limits to achieve the extraordinary. Bridges are among humanity's oldest and most striking megaprojects, serving as vital arteries linking geographic barriers and catalyzing economic and social integration. The engineering of the world's longest and tallest bridges exemplifies the extraordinary scale, precision, and innovation megaprojects demand, marrying aesthetics with unmatched structural integrity. Consider the Danyang Kunshan Grand Bridge in China, stretching an astonishing 164.8 kilometers as the longest bridge in the world. Constructed along the Beijing-Shanghai high-speed railway, it traverses a combination of water bodies, rice paddies, and urban areas. Designing a structure of such length required meticulous geotechnical surveys addressing soft soil consolidation, settlement control, and seismic resilience. The bridge supports high-speed trains exceeding 300 kilometers, demanding extremely tight tolerances on alignment and vibration suppression. Hundreds of thousands of concrete piles anchor its massive spans, and precast segmental construction accelerated the timetable substantially, while preserving quality. At the opposite extreme, the Millau Viaduct in southern France soars nearly 343 meters above the Tarn River Valley, making it the tallest bridge on Earth. This cable-stayed marvel required working atop deep gorges with unpredictable winds, sharp weather changes, and complex geology. Its slender, yet robust piers distribute loads effectively, while aerodynamic deck designs address extreme vortex shedding and pulsations induced by Mediterranean winds. Construction involved innovative launching methods, moving deck sections forward atop temporary supports, avoiding intrusive scaffolding in the valley. The project showcases an elegant integration of engineering, landscape, and architecture to create a structure both functional and visually iconic. Suspension bridges push engineering limits through their flexibility, length, and the massive tensile forces in their main cables. The Akashi Kaikyo Bridge in Japan, the longest suspended span at 1,991 meters, connects Kobe to Awaji Island, across a notoriously seismic and typhoon-prone strait. Engineers designed its cables from over 300,000 kilometers of wire, arranged with redundancies to endure corrosion, fatigue, and earthquakes. The bridge incorporates intricate damping systems, reducing oscillations experienced during windstorms, as demonstrated when the Great Hanshin earthquake struck during construction, delaying progress but validating seismic resilience. Each bridge type arc cable stayed, suspension, beam represents a tailored solution to site constraints, span requirements, and load demands. Designing mega-span bridges demands precise estimation of construction loads, self-weight, live loads, and environmental effects, such as thermal expansion, shrinkage, wind, and earthquakes. Finite element modeling captures interactions within complex structures, informing how stresses distribute across cables, decks, towers, and foundations. These analyses guide material selection, cross-sectional dimensions, and joint detailing. Foundations underpin bridge longevity and safety, often requiring deep drilled shafts or piles driven into bedrock hundreds of meters below water or soil. Underwater construction demands caissons, cofferdams, and specialized marine equipment capable of precision placement amidst currents and limited visibility, protecting against scour. The erosion of sediment around piers by water flow necessitates protective aprons or innovative riprap designs. Material innovations have revolutionized bridge engineering. High-performance concrete mixes incorporate additives enhancing durability against chloride attacks, and freeze-thaw cycles vital for bridges spanning saline or cold environments. Ultra-high-performance steel alloys provide exceptional strength and toughness, enabling slender and elegant structural members. Composite materials and corrosion-resistant coatings extend service lives while reducing maintenance costs. Construction logistics require orchestrated planning involving factories producing segments, transportation by barges or heavy lift vehicles, and synchronized assembly leveraging cranes, cable cranes, or incremental launching. Safety is paramount, with protocols minimizing risks to thousands of workers operating at dizzying heights over water and terrain. Drone inspections and robotic monitoring increasingly supplement human observation, providing real-time data on structural health during construction and operation. Sustainability demands consideration of environmental impacts, from habitat disruption during pier placement to emissions produced during manufacturing and transport of materials. Engineers collaborate with ecologists to mitigate adverse effects through seasonal scheduling, fish passage installations, and habitat restoration projects complementing bridge development. Beyond technical complexity, mega bridges exemplify community and political ambitions. They symbolize progress, economic opportunity, and connectivity enhancing regional development. Stakeholder engagement ensures cultural sensitivity and social acceptance, vital for projects spanning indigenous lands or contested regions. Transparent communication and environmental assessments foster trust and partnership. These immense undertakings reveal the orchestration of science, art, management, and diplomacy required for megaproject success. Each span tells a unique story of human ingenuity responding to physical and societal challenges with innovative engineering and persistent endeavor. Beneath our feet and under bodies of water, vast underground arteries, tunnels, link regions, cities, and transport networks, constituting some of the most technically demanding megaprojects ever undertaken. These subterranean marvels solve pressing constraints in topography, urban density, and environmental preservation, yet impose extraordinary engineering challenges involving geology, hydrology, and spatial logistics at unprecedented scales. Consider the Channel Tunnel, or Channel, connecting the United Kingdom and France beneath the English Channel. Spanning 50.45 kilometers with a 37.9 kilometer undersea stretch, it represents one of the longest and deepest operational tunnels worldwide. Its construction embodied a colossal feat of coordination between two nations, thousands of engineers and workers, and cutting-edge tunneling technology. Engineers contended with highly variable chalk-marl geology, saline water intrusion, and ground settlement risks beneath a busy shipping lane. Tunnel boring machines, TBMs, with enormous cutter heads mechanically excavated while simultaneously installing precast concrete lining segments. Sophisticated ventilation, emergency access galleries, and high-speed rail infrastructure completed the system seamlessly linking London with Paris. In mountainous terrain, the Gotthard Base Tunnel in Switzerland breaks records as the world's longest railway tunnel at 57 kilometers, running beneath the Swiss Alps, running at depths of up to 2,300 meters. It demanded an exceptional geological survey program to map faults, rock hardness zones, and groundwater inflows. The precision drive involved parallel bores blasted and mechanized by hybrid TBMs equipped with advanced sensor arrays for real-time condition monitoring to handle immense thermal gradients caused by geothermal heat. Engineers incorporated ventilation shafts and monitored thermal expansion effects on tunnel lining and track infrastructure. The tunnel drastically improves freight and passenger transit efficiency, reducing alpine road congestion and emissions. Urban environments add another layer of complexity with tunnel megaprojects carving beneath existing structures, utilities, and historical artifacts. The Tokyo Metro Chiyoda Line extension traversed densely built neighborhoods with minimal surface disruption. Ground freezing and jet grouting stabilized soil before excavation to prevent settlement affecting skyscrapers and historical sites. Continuous structural health monitoring and meticulous construction sequencing ensured safety amidst constant commuter activity overhead. Tunnel design rigorously addresses geological variability. Rock compositions fluctuate from hard granite to soft sedimentary clays, each requiring distinct excavation techniques and support systems ranging from rock bolts and sprayed concrete to steel ribs and segmental liners. Predicting water ingress guides waterproofing strategies, incorporating waterproof membranes, drainage galleries, and ceiling collars. Ventilation is critical for worker safety and long-term tunnel operation, maintaining air quality, temperature, and smoke control. Complex ventilation shafts, fans, and airflow modeling ensure sufficient exchange in tunnels, often housing high-speed trains or motorways. Fire safety engineering integrates escape routes, pressurized safe refuges, automated detection and suppression systems, coupled with command and control centers, coordinating rapid emergency response, challenges magnified by tunnel length and access limitations. Logistics in tunnel construction, megaprojects require continuous excavation debris removal via conveyor belts or rail cars, material supply chain management, and workforce rotation planning to maintain 24/7 operations. Remote monitoring technologies and autonomous machines increasingly assist in these endeavors. Environmental stewardship assures minimal impact on groundwater regimes and surface ecosystems. Engineers engage hydrogeologists to model dewatering effects and implement recharge measures post-construction, preserving aquifers and wetlands dependent on delicate groundwater balances. Advancements in TBM technology allow customized cutter heads, quasi-intelligent control systems adapting pressure and vibration to minimize damage in sensitive strata. These machines often dwarf football fields in length, housing complex instrumentation and operator cabins. Megaprojects integrating tunnels contribute vital resilience to transport and utility networks, enhancing flood control, power transmission, and telecommunications through underground conduit corridors. Beyond transport, tunnels encompass water diversion and supply projects, such as the Snowy Mountains Hydro Scheme in Australia, connecting mountain reservoirs with power stations through 145 kilometers of tunnels, and sewage management megatunnels underlying metropolitan sewer systems, managing millions of residents' waste. Urban tunneling projects utilize slurry shield TBMs to stabilize weak soil layers while ensuring minimal surface subsidence, a technology crucial for expanding metro systems in cities like New York, Paris, and Delhi, under crowded, brittle soil strata. In sum, tunnel megaprojects exemplify engineering's confrontation with geological uncertainty, spatial constraints, and safety imperatives, weaving together innovation and resilience beneath the surface of daily life. Skyscrapers stand as the quintessential symbol of megaproject ambition, thrusting vertical boundaries skyward and embodying engineering's relentless quest to redefine the horizon. These colossal constructions challenge not only gravity, but also material limitations, wind dynamics, seismic forces, and urban integration, forcing advances in structural systems, construction methods, and sustainability. At the apex of modern skyscraper engineering is the Burj Khalifa in Dubai, which at 828 meters remains the tallest building globally. Its design evolved through extensive wind tunnel testing and structural optimization to combat intense desert winds and thermal gradients. The building's unique stepped architecture disperses wind vortices that could cause oscillations harmful to occupant comfort and structural integrity. Deep foundations employ piles reaching depths of 50 meters into compressive bedrock, anchoring the superstructure. High-performance concrete mixes capable of curing in extreme heat provide the backbone, while ultra-strength steel reinforcements enable slender but resilient columns. Mechanical and electrical systems integrate sophisticated vertical transportation, over 60 elevators with speeds exceeding 10 meters per second, and advanced fire protection engineered for unprecedented evacuation challenges. The engineering rigor involved in these skyscrapers extends into seismic design, especially in earthquake-prone regions like Tokyo's Toranomon Hills or the Shanghai Tower. These structures incorporate tuned mass dampers, giant pendulum-like systems designed to counteract sway induced by wind or tremors, enhancing occupant comfort and safety. Base isolators and energy dissipation systems further reduce seismic forces transmitted to the building, protecting both structure and inhabitants. Structural innovations include the use of mega columns and high-strength composite materials to create rigid cores and perimeter frames, distributing lateral loads efficiently. Outrigger and belt truss systems link cores to perimeter columns, increasing bending resistance and reducing deflections. Engineers utilize finite element analysis to model nonlinear behaviors under combined loads, ensuring safety margins while optimizing material use. The construction of super-tall buildings requires advanced planning and precision logistics. Prefabricated modular units expedite assembly while minimizing on-site labor in constrained urban environments. Concrete pumping to record heights and automated climbing formwork systems facilitate rapid floor-by-floor construction in alignment with safety protocols. Continuous real-time monitoring of verticality and load distribution safeguards against accumulated deviations during erection. Sustainability considerations reshape skyscraper design, with green roofs, photovoltaic panels, and rainwater harvesting integrated seamlessly. High-performance glazing and dynamic shading systems regulate solar gain and optimize daylight usage, reducing energy demands. Waste heat recovery and district cooling connections improve operational efficiency. Urban planning for megatall buildings balances density with public space enhancements, transit connectivity, and emergency egress planning, integrating mixed-use environments, shopping, residential, office, cultural spaces within skyscrapers promotes social interaction, reduces urban sprawl, and enhances resilience. Skyscraper megaprojects also drive innovation in material science. Ultra-high-strength concrete formulas, corrosion-resistant steel alloys, fire-resistant composites, and smart materials monitoring structural health. Sensor arrays embedded in critical members track stresses, deflections, and vibrations, feeding predictive maintenance systems essential for safety and longevity. Iconic towers reflect cultural identity and technological prowess, symbolizing progress and futuristic visions. Their silhouettes redefine skylines and inspire architectural creativity, guided by, but often pushing beyond, engineering feasibility. Globally, cities like New York, Shanghai, Dubai, Seoul, and Mumbai showcase these vertical megaprojects as engines of economic growth and urban transformation, demanding multidisciplinary collaboration encompassing engineering. Emergent concepts envision even taller structures, tens of kilometers high, and floating or space elevator megaprojects posing engineering enigmas in materials strength, stability, and construction. This chapter of megaproject engineering reveals a fusion of physics, innovation, and human aspiration, materialized in breathtaking verticality that challenges nature and reshapes the urban fabric. Transportation megaprojects represent monumental undertakings that reshape regional, national, and global connectivity, stimulating economic growth and social mobility on vast scales. These enterprises encompass sprawling high-speed rail networks, expansive airport complexes, and integrated urban transit systems, each demanding extraordinary engineering expertise, coordination, and innovation. High-speed rail megaprojects stand at the forefront of sustainable transportation, propelling passengers at velocities exceeding 300 kilometers, while connecting metropolitan hubs with unprecedented speed and efficiency. China's expansive high-speed network, now the largest globally, features engineering marvels like the Beijing-Shanghai corridor, spanning over 1,300 kilometers and integrating bridges, tunnels, viaducts, and state-of-the-art signaling systems. This system demanded harmonizing multiple disciplines: precision track alignment with tolerances of mere millimeters, aerodynamically optimized train sets, minimizing frictional losses, and electromagnetic interference shielding, ensuring safe, uninterrupted communications. Constructing such vast networks involved overcoming geotechnical and environmental challenges, building trans-reach bridges over flood-prone zones, tunneling under mountains and urban sprawls, and addressing seismic fault lines through base isolation and flexible track designs. Ensuring minimal disruption to communities and sensitive ecosystems required sophisticated planning with mitigation strategies like wildlife crossings, noise barriers, and pollution control during construction. Complex track switching yards, maintenance depots, and integration with conventional rail segments further expanded the project footprint. Engineers devised modular construction methods, prefabricating track components and station structures to accelerate build times while preserving quality. Advanced track laying machines monitored geometry and tension in real time to maintain safety at extreme speeds. Mega airports, such as Dubai International, Beijing Daxing, and Istanbul Airport, represent other pillars of transportation megaprojects, engineered to handle tens of millions of passengers and cargo tons annually. These sprawling complexes incorporate multiple runways with precision-paved surfaces engineered to withstand extended aircraft loading cycles and temperature fluctuations. Their terminal buildings blend architectural grandeur with logistical efficiency, featuring expansive baggage handling systems, automated people movers, and cutting-edge security and operational technologies. Airport construction contended with geotechnical variability, necessitating deep soil improvement methods and rigid pavement designs accommodating heavy wheel loads. Sophisticated air traffic control systems sync with approach lighting and radar for enhanced situational awareness. Sustainability interventions like solar arrays, rainwater harvesting, and energy-efficient HVAC systems address environmental footprints. Urban transit megaprojects, including metro, light rail, and bus rapid transit systems, focus on addressing congested cities' needs for reliable, clean, and accessible mass movement. Megaprojects like London's Crossrail and Delhi Metro involved extensive underground tunneling, elevated track systems, and state-of-the-art automation technologies, delivering high-frequency services. Integrating multiple modes requires fare system unification, coordinated schedules, and shared infrastructure. Advanced signaling systems utilize communications-based train control for tight headways and improve safety. Station design emphasizes passenger flow optimization using biomechanics-informed layouts, wayfinding technologies, and universal accessibility. Rolling stock incorporates lightweight materials, regenerative braking, and passenger amenities, enhancing comfort and efficiency. ICT integration enables real-time monitoring of fleet condition, demand forecasting, and incident management, optimizing operations and passenger experience. Construction management of transportation megaprojects tackles massive workforce deployment, requiring stringent safety programs, materials, logistics, and environmental management to mitigate emissions and waste. Public engagement and stakeholder collaboration align project goals with societal needs and expectations. Financing such megaprojects blends public funds, private investment, and international cooperation, necessitating transparent governance and risk-sharing frameworks, sustaining long project life cycles. These transportation megaprojects are transformational, their engineering complexities highlighting human capacity to orchestrate mega-scale systems, delivering profound societal impact through rapid, reliable, and sustainable mobility solutions. Energy megaprojects represent the backbone of modern civilization, harnessing natural forces and scientific principles to power cities, industries, and technological progress on unprecedented scales. These colossal ventures encompass sprawling hydroelectric dams, advanced nuclear power complexes, and massive renewable energy parks, each demanding unparalleled integration of engineering disciplines, environmental stewardship, and societal engagement. At the apex stands the Three Gorges Dam in China, the world's largest hydroelectric facility, spanning over 2 kilometers across the Yangtze River and towering 185 meters high. The dam serves multiple critical roles: flood control, hydroelectric power generation, and navigation improvement. The engineering dauntingly confronted immense hydrological variability, sediment management issues, and ecological impacts. Detailed hydrodynamic modeling simulated flood events and sediment transport, informing spillway design capable of regulating enormous river discharges. The dam's powerhouse integrates 34 massive turbines totaling 22,500 megawatts of generating capacity, the mechanical heart engineered for high efficiency, durability under turbulent water flows, and ease of maintenance. Construction entailed diverting the mighty Yangtze, excavating more than 27 million cubic meters of earth and rock, and relocating over 1 million residents across affected areas. Complex navigation lock systems accommodate large vessels, preserving river trade vital to regional economies. Nuclear megaprojects blend thermodynamics, material science, and safety engineering into sophisticated energy generation complexes. The Kashiwazaki Kariwa plant in Japan, one of the world's largest nuclear power stations, incorporates multiple boiling water reactors with combined outputs exceeding 7,900 megawatts. Designers contend with extreme seismic activity, incorporating advanced isolation techniques, redundant cooling systems, and layered containment structures engineered to prevent radioactive release even in catastrophic events. Reactor cores utilize enriched uranium fuel assemblies optimized for thermal neutron flux, and control systems deploy fail-safe shutdown protocols managed via digital instrumentation and real-time monitoring. The plant's cooling towers and turbine generators integrate thermodynamic cycles tuned for efficiency and environmental compliance. The decommissioning and waste management phases embody decades-long megaprojects themselves, requiring engineered solutions for spent fuel storage and radioactive waste containment. Renewable energy megaprojects transform landscapes with fields of photovoltaic panels, wind turbines, and energy storage facilities, steering the transition to sustainable power amid climatic urgency. The Gansu wind farm in China, sprawling over 20,000 square kilometers, exemplifies such scale, comprising thousands of wind turbines connected by extensive electrical infrastructure to regional grids. Engineering challenges include optimizing turbine spacing to minimize wake interference, integrating variable output with grid stability requirements, and minimizing maintenance in remote, often harsh environments. Foundations accommodate complex soil and permafrost conditions, while carbon fiber blades utilize advanced composites to balance strength, flexibility, and weight. Sophisticated supervisory control and data acquisition SCADA systems provide real-time performance analytics, predictive maintenance, and fault detection. Large-scale solar farms utilize high-efficiency photovoltaic modules, employing multi-junction cells, bifacial panels, and tracking mechanisms enhancing solar capture throughout the day. Precise geometrical layouts optimize land use, while maintaining accessibility and shading control. Water use management strategies incorporate dry cooling and dust mitigation techniques critical in arid locations. Energy storage megaprojects are vital complements to intermittent renewable sources, pumped hydro storage facilities, battery megafarms using lithium-ion or flow battery technologies, and hydrogen production plants integrate complex electrochemical, mechanical, and control systems to balance supply-demand and ensure grid reliability. Scaling such systems involves thermal management, degradation monitoring, and integration with digital energy management platforms. Transmission infrastructure. Megaprojects underpin energy delivery featuring ultra-high voltage alternating current UHVAC and direct current HVDC lines spanned over vast distances. Engineering innovations in conductor materials, tower design, and substation automation reduce energy losses and improve resilience against environmental extremes. Environmental and social considerations in energy megaprojects drive comprehensive impact assessments addressing biodiversity protection, water quality, resettlement processes, and cultural heritage preservation. Adaptive mitigation measures include fish passage installations in dams, community benefit sharing frameworks, and rigorous stakeholder engagement throughout project life cycles. Safety assurances permeate all stages, deploying multiple redundancy layers, emergency response planning, and international regulatory compliance adhering to standards from entities like the International Atomic Energy Agency or the International Hydropower Association. Financing energy megaprojects involves complex risk evaluations, long-term contracts, and multi-stakeholder partnerships, balancing technological uncertainty with societal imperatives for reliable, clean energy. The synthesis of cutting-edge science, societal collaboration, and technological perseverance evident in energy megaprojects showcases humanity's capacity to engineer power for billions sustainably and safely. Water, the lifeblood of civilization, shapes human settlement, agriculture, industry, and ecosystems. Large-scale water management megaprojects stand as quintessential engineering endeavors balancing the resources' abundance and scarcity, control and freedom. Vast reservoirs, irrigation networks, flood control infrastructures, and water transfer schemes underpin socioeconomic development for billions, requiring colossal collaboration, innovation, and foresight. The engineering spectacle of the Gotthard Water Tunnel in Switzerland exemplifies this domain's technical challenges, stretching over 130 kilometers at depths up to 2,300 meters beneath the Alps. It diverts mountain waters to hydropower plants, facilitating renewable electricity production while preserving natural landscapes. Tunneling under complex metamorphic and sedimentary formations integrated hydrogeological assessments, guiding tunnel diameters, gradients, and lining thicknesses to suppress leakage and prevent erosive piping. The tunnel embodies intricate hydraulic engineering, managing pressure surges and flow rate regulation through surge tanks and valve systems embedded in the conduit. Irrigation megaprojects catalyze agricultural revolutions by transforming arid and semi-arid lands into fertile fields, fueling food security for growing populations. The Indira Gandhi Canal in India, over 650 kilometers long, channels water from the Himalayan-fed Sutlej River into the Thar Desert. Its construction demanded grand-scale engineering. Immense canal embankments stabilized through geotechnical methods, numerous aqueducts and siphons crossing rivers and roads, and advanced flow control structures to optimize water distribution. Maintenance efforts combat sediment deposition and seepage, involving lining technologies and vegetation management. The canal facilitates double cropping patterns and supports rural livelihoods, but also poses sustainability challenges from salinization and changing rainfall patterns addressed by adaptive management. Flood control megaprojects integrate civil, hydraulic, and environmental engineering to protect urban centers and agricultural zones from devastating inundations. The Netherlands Delta Works System, a comprehensive array of dams, sluices, storm surge barriers, and levees, stands as a masterpiece of integrated water defense. After the catastrophic North Sea flood of 1953, engineers designed automated gates responsive to tidal and meteorological data, massive dams with movable sections allowing river discharge under normal conditions, yet sealing storm surges. The system balances flood protection with ecological connectivity, employing fish passages and wetland restoration programs. Complex modeling simulates sea level rise and extreme weather scenarios to inform adaptive infrastructure upgrades. Mega reservoir projects like the Hoover Dam on the Colorado River play multi-dimensional roles: hydropower generation, water supply, flood control, and recreation. The Hoover Dam's arch-gravity design required precise engineering calculations, combining structural mechanics and concrete technology to withstand enormous hydraulic loads. Cooling systems mitigated heat of hydration during curing of millions of cubic meters of concrete, a critical process preventing structural cracking. Reservoir sedimentation, a long-term concern, reducing capacity. necessitates coordinated upstream watershed management strategies. Water transfer megaprojects traverse vast distances, moving water from surplus to deficit areas to support urbanization and irrigation. The California State Water Project, spanning over 700 kilometers, conveys water from the northern Sierras to the populous south. Engineering complexities include pump stations lifting millions of liters per second over mountain ranges, extensive canal and pipeline networks with leak detection and pressure regulation systems, and environmental mitigation efforts preserving aquatic habitats. Desalination megaprojects address freshwater scarcity by converting seawater into potable water using reverse osmosis or thermal distillation. The Ras Al Khair plant in Saudi Arabia, one of the world's largest, integrates cogeneration of electricity and water, employing energy recovery devices optimizing efficiency. Engineering challenges include corrosion-resistant materials, brine disposal management, and scalability within limited land footprints. Integrated watershed management megaprojects combine infrastructure with policy and data systems. Remote sensing, geographic information systems, GIS, and hydrological models aid in allocating water resources, predicting shortages, and optimizing reservoir operations under climatic variability and competing demands. Sustainability frameworks in water megaprojects emphasize ecosystem service valuations, equitable water sharing, and participatory governance. Social impacts include displacement, cultural site preservation, and livelihood transitions, addressed through transdisciplinary stakeholder engagement. Safety engineering ensures dam and levee stability through seismic assessments, structural monitoring with fiber optics and piezometers, and emergency action plans designed for rapid response to incidents. Financing and management mitigate megaproject risks via phased implementation, public-private partnerships, and international cooperation, essential given long time horizons and capital intensity. Water megaprojects underscore engineering's role in shaping hydrological regimes to provide secure, resilient, and equitable access to humanity's most vital resource, threading complex physical, social, and environmental systems. Urban infrastructure megaprojects articulate the beating heart of thriving metropolises, orchestrating the seamless web that supports modern life. Massive ports facilitating global trade, expansive logistics hubs, optimizing supply chains, and burgeoning smart city frameworks, digitally weaving efficiency and sustainability into urban fabric. These endeavors embody the integration of civil, electrical, mechanical, and information engineering disciplines, demanding visionary planning and relentless technical precision. Megaports, gateways of globalization, fulfill the critical role of handling colossal cargo volumes with speed, reliability, and environmental stewardship. The Port of Shanghai, the busiest container port worldwide, spans over 3,600 hectares, featuring advanced quay cranes capable of servicing ultra-large container vessels up to 24,000 TEU capacity. Engineering challenges include constructing deep water berths dredged to depths exceeding 15 meters, reinforced quay walls designed to withstand dynamic impact loads from berthing vessels, and extensive storage yards integrating automated stacking cranes and guided vehicles. Sophisticated terminal operating systems coordinate container movements across sea, rail, and road modalities, utilizing RFID tracking and real-time analytics, optimizing throughput and turnaround time. Construction of such infrastructure involves enormous earth moving, with reclamation extending coastline, soil stabilization using vibrocompaction, and deep soil mixing to ensure ground-bearing capacity, and utilities installation synchronized with port facility expansion. Environmental measures include sedimentation control during dredging, ballast water treatment systems preventing invasive species, and emissions mitigation through electrification of gantry cranes and hybrid harbor tugs. Logistics hubs underlying the supply chain command sprawling complexes combining warehousing, cross-docking, customs clearance, and distribution centers. Facilities like the Dubai Logistics City integrate multimodal terminals connecting maritime, air, and terrestrial transport, optimized by advanced warehouse management systems, employing robotics and AI-guided order picking. Engineering these logistics megaprojects demands efficient layout planning, minimizing travel distances, and optimizing storage density, supported by IT infrastructure, ensuring traceability, dynamic inventory management, and seamless intermodal transfers. Energy systems incorporate microgrids powered by solar photovoltaic arrays and energy storage, ensuring operational resilience. Intelligent building management systems regulate HVAC, lighting, and security, reducing operational costs and environmental footprint. These hubs are designed for scalability and adaptability to evolving market and technological trends. Smart city frameworks represent an emerging class of urban megaprojects, transforming physical infrastructure through digital integration, aimed at efficiency, sustainability, and quality of life. Deploying citywide sensor networks with IoT devices collects granular data, monitoring energy consumption, traffic flow, air quality, and public safety metrics. Centralized urban management platforms use data analytics and machine learning to prioritize resource allocation, predictive maintenance of infrastructure, and emergency response coordination. Communication infrastructure, 5G networks, fiber optic grids, form the backbone, facilitating high-speed data exchange critical for autonomous vehicles, telemedicine, and decentralized energy trading. Intelligent transportation systems coordinate smart traffic lights, connected vehicles, and shared mobility services, reducing congestion and emissions. Waste management evolves with sensor-equipped bins and optimized collection routing, improving recycling rates and operational efficiency. Urban water systems deploy smart metering, leak detection technologies, and adaptive pressure management, reducing losses and ensuring equitable allocation. Energy infrastructure incorporates distributed renewables, demand response programs, and electric vehicle charging networks, balancing grid loads. Citizen engagement platforms foster participatory governance through transparent data dashboards, feedback channels, and digital public services, enhancing accountability and inclusivity. Challenges arise in cybersecurity, data privacy, interoperability of heterogeneous systems, and equitable access to digital services. Engineers work with policymakers and social scientists establishing ethical frameworks and resilient architectures protecting urban digital commons. Examples such as Singapore's Smart Nation initiative and Barcelona's urban innovation programs showcase integrated megaprojects blending connectivity, sustainability, and empowerment, transforming cities into responsive living systems. Construction of such large-scale urban megaprojects requires massive coordination among stakeholders, phased implementation minimizing disruption, and adaptive management, addressing evolving technology standards and citizen needs. These endeavors redefine urban life through the fusion of infrastructure and digital intelligence, promising resilient, efficient, and human-centered cities ready for 21st century challenges. Aerospace megaprojects occupy the literal and figurative frontier of engineering, where human ambition transcends terrestrial boundaries to explore the vastness of space, and where the design, construction, and operation of complex systems confront harsh environments, extreme conditions, and stringent safety requirements. These endeavors encompass launch facilities, orbital platforms, interplanetary missions, and associated ground support infrastructures. Each element demands confluence of mechanical, structural, electrical, thermal, and software engineering at unprecedented integration levels, pushing the limits of materials, systems reliability, and mission assurance. At the heart of aerospace megaproject engineering lies launch complexes designed to facilitate the safe, efficient, and reliable deployment of spacecraft into orbit and beyond. Facilities like the Kennedy Space Center in Florida or the Baikonur Cosmodrome in Kazakhstan are vast sprawling hubs, managing multitudes of systems, vehicle assembly buildings housing gigantic rockets, transporters moving vehicles over kilometers, flame trenches designed to deflect hundreds of tons of rocket exhaust, myriad ground support equipment GSE providing fueling, power, telemetry, and command, and environmental control systems maintaining optimal conditions. These complexes require precise infrastructure engineering. Foundations must absorb tremendous dynamic loads and vibrations. Electrical substations must protect sensitive electronics. And infrastructures are hardened against environmental factors, like hurricanes or extreme cold. Rocket technology at the core pushes material science and propulsion engineering. Liquid-fueled engines demand turbopumps capable of delivering high-pressure propellants reliably while withstanding thermal and mechanical stresses. Solid rocket boosters embody compact, high-thrust devices engineered for precise burn characteristics. Recent developments pursue reusable rocket stages. Falcon 9 from SpaceX demonstrates rapid landing and refurbishment technologies, requiring robust control systems, durable thermal protection, and precise structural reinforcements, able to survive multiple extreme re-entry cycles. Engineers optimize thrust vector control systems, integrating complex gimbaling mechanisms, differential throttling, and electromagnetic actuators, augmenting vehicle stability. Orbital platforms like the International Space Station, ISS, exemplify human-made habitats, engineering at extremes. The modular ISS spans over 100 meters, with interconnected pressurized modules supporting life in microgravity for decades. Engineering challenges include micrometeoroid shielding, radiation protection, thermal control balancing solar heating, and deep space cooling, and redundancy in life support systems to ensure continuous oxygen, carbon dioxide removal, and water recycling. The station's power systems utilize vast solar arrays generating kilowatts of electricity, monitored and regulated through sophisticated power electronics. Robotic arms conduct maintenance and support docking spacecraft arrivals, orchestrated via advanced control algorithms and teleoperation protocols. Interplanetary missions amplify complexity exponentially. Designing Mars rovers like Curiosity or Perseverance entails integrating propulsion, autonomous navigation, scientific instrumentation, communications over millions of kilometers with latency, and thermal management in extreme planetary climates. Engineers develop entry, descent, and landing sequences incorporating parachutes, retro-rockets, and sky cranes to softly deposit payloads onto alien surfaces, a choreography of technologies tested through extensive simulations. Radiation hardening of electronics, energy harvesting via radioisotope thermoelectric generators or solar panels, and dust mitigation systems further embody layered engineering demands. Sample return missions incorporate containment and sterilization engineering, preventing cross-contamination. Ground support for deep space missions engages antenna arrays globally, capable of detecting faint signals across interplanetary distances. Supported by data processing and error correction methods, ensuring integrity. Facilities must manage vast volumes of telemetry and scientific data flowing continuously, necessitating resilient IT infrastructure and adaptive software systems. Software engineering underwrites the entire aerospace megaproject lifecycle. Flight control software operates under demanding real-time constraints with stringent certification processes ensuring safety and fault tolerance. Mission planning and simulation software aid design verification, training, and contingency management. Safety pervades every stage, from human-rated vehicle designs incorporating escape systems, redundant avionics, and extensive testing campaigns, to unmanned missions embedding fault detection and autonomous recovery capabilities. Certification protocols involve regulatory agencies worldwide, standardizing interface specifications, quality assurance, and risk assessments. Sustainability considerations grow with debris mitigation strategies, reusable vehicle initiatives, and minimizing environmental impact at launch sites, reflecting broader societal imperatives. Financial planning underpins mega-project management, addressing extended development times, international collaborations and technology uncertainties, iterative design, phase development, and risk-sharing arrangements improve viability. Aerospace megaprojects symbolize humanity's daring quest into the cosmos, a testament to synergistic technical excellence, international partnership, and vision transcending borders. These vast enterprises exemplify engineering's capacity to confront and master the hostile frontier of space, delivering breakthroughs benefiting science, technology, and ultimately human exploration. The integration of advanced digital technologies underpins the development, execution, and operation of megaprojects, revolutionizing traditional engineering paradigms through enhanced precision, informed decision-making, and real-time adaptability. These digital innovations spanning building information modeling, BIM, digital twins, artificial intelligence, AI, machine learning ML, cloud computing, and the Internet of Things IoT deliver unprecedented capabilities transforming megaproject workflows from conception to commissioning and beyond. Building information modeling constitutes a foundational digital methodology, providing comprehensive three-dimensional representations, embedding geometric, spatial, and semantic data of megaproject components. Unlike conventional draft-based design, BIM facilitates interdisciplinary collaboration by integrating architectural, structural, mechanical, electrical, and civil engineering models into a unified environment. This cohesion enables clash detection algorithms to identify spatial conflicts early, reducing costly rework during construction. Parametric design attributes empower dynamic updates, where modifications propagate through related elements, maintaining model consistency. BIM frameworks incorporate Schedule 4D and Cost 5D data linking project timelines and budgets with physical components, fostering holistic project planning and resource optimization. Digital twins extend BIM principles into operational contexts, creating virtual replicas of physical infrastructure that receive continuous real-time data through embedded sensors and control systems. These interactive models simulate performance under varying conditions, allowing predictive maintenance, scenario testing, and informed asset management. For hydroelectric dams, digital twins monitor structural health parameters such as concrete strain, seepage rates, and turbine vibrations, enabling early detection of anomalies and reducing downtime. In urban transport hubs, digital twins model passenger flow fluctuations, adjusting operational strategies dynamically. Development requires integrating IoT networks with cloud-based analytic platforms, ensuring data fidelity, latency minimization, and security resilience. Artificial intelligence and machine learning algorithms penetrate various project phases, augmenting human capacity to analyze vast datasets, optimize designs, and automate complex decision processes. For example, AI-driven generative design explores expansive parametric design spaces, evolving thousands of configurations based on performance criteria such as structural strength, cost efficiency, and environmental impact, ultimately proposing novel solutions beyond conventional engineering intuition. In construction management, ML analyzes sensor data streams and historical records to identify risk patterns such as equipment failures, labor bottlenecks, or weather disruptions, enabling proactive mitigation. Natural language processing assists in document management, extracting critical contract terms and compliance requirements automatically. Cloud computing offers scalable computational power and storage, facilitating collaborative workflows across geographically distributed teams. Cloud platforms support versioning control, simultaneous multi-user editing, and integration of disparate software tools, ensuring model coherence. Parallel computing enables massive finite element analyses, modeling nonlinear complex behaviors under realistic loading with precision unattainable on standalone hardware. Accessibility from mobile devices equips site engineers with real-time data access, bridging information gaps between field and office. The Internet of Things constitutes a sensory fabric woven throughout megaprojects. Embedded sensors measure temperature, humidity, vibration, load, displacement, and energy consumption, continuously feeding digital systems a high-resolution operational picture. Wearable health monitors for workers enhance safety management by tracking fatigue, location, and exposure to hazardous substances. Automated drone inspections, equipped with high-definition cameras and LiDAR, acquire detailed condition data from inaccessible or dangerous locations, supplemented by machine vision analysis, detecting cracks, corrosion, or deviations instantaneously. Sophisticated simulation environments couple physics-based computation with AI-driven surrogate models, enabling rapid performance assessments during design iterations. Virtual reality, VR, and augmented reality, AR technologies immerse stakeholders into digital project environments for enhanced spatial understanding, design validation, training, and remote collaboration. These immersive experiences reduce errors and improve communication across diverse disciplines and stakeholder groups. Cybersecurity frameworks protect increasingly interconnected megaproject digital ecosystems against attacks targeting intellectual property, operational continuity, or safety-critical systems. Multi-layered encryption, access control, anomaly detection, and contingency planning constitute essential defense strategies. Data governance policies underlie responsible megaproject digitization, ensuring data quality, ownership rights, privacy, ethical use, and compliance with regulatory mandates. Transparent open data initiatives foster community engagement and innovation while safeguarding sensitive information. Despite the transformative potential, digital technologies do not replace human expertise. Rather, they augment engineering judgment, creativity, and ethical accountability. Effective digital integration requires workforce upskilling, process re-engineering, and adaptive organizational cultures embracing continuous learning. Ultimately, digital megaproject engineering transcends traditional silos, blending virtual and physical realms into cohesive, intelligent systems capable of navigating the complexity, scale, and dynamic nature of today's infrastructure and technological challenges. This fusion of human ingenuity and digital power paves the way for safer, smarter, more efficient megaprojects, shaping resilient futures for communities worldwide. Materials innovation forms the bedrock upon which the towering ambitions of megaproject engineering ascend. From the foundations deep beneath colossal dams to the slender spires piercing metropolitan skies, the quest for materials exhibiting superior strength, durability, sustainability, and adaptability drives breakthroughs that redefine what megaprojects can achieve. This chapter illuminates the remarkable transformations wrought by next-generation materials science, bridging molecular engineering and macro-scale structural exigencies. High-performance concrete HPC variants revolutionize structural engineering in megaprojects, delivering compressive strength exceeding 120 megapascals, enhanced toughness, and improved resistance to environmental degradation. These concretes integrate supplementary cementitious materials like silica fume and fly ash, modifying microstructure to reduce porosity and inhibit chloride ingress, critical for durability in marine or de-icing salt environments. Advances in mixed design optimize rheology and placing characteristics, enabling self-compacting concrete SC applications critical for dense reinforcement zones. Moreover, nanotechnology introduces engineered nanoparticles such as titanium dioxide and nanosilica that improve hydration kinetics and impart self-cleaning, photocatalytic, and antimicrobial properties, prolonging service life in aggressive urban atmospheres. Ultra-high performance, fiber-reinforced concrete UHPFRC exemplifies material evolution combining ultra-fine powders, optimized gradation, and continuous microfiber reinforcement, polyvinyl alcohol or steel fibers, yielding tensile strength surpassing 10 MPa and exceptional ductility. This allows the design of slender, lightweight structural components with superior energy absorption under dynamic loading, dovetailing with seismic resilience needs in megaprojects situated in high-risk zones. In steel innovation, developments include advanced high-strength steels, AHSS, featuring improved yield strength and toughness facilitating reduced member sizes and weights without compromising safety. Corrosion-resistant alloys and protective coatings extend the lifespan of exposed structural elements subjected to marine or industrial environments. Weathering steels naturally form patinas, reducing maintenance demands in bridge and offshore structures. Metallurgical processes, producing ultra-fine grain microstructures, enhance fatigue resistance, critical for repetitive loading, encountered in bridges, cranes, and turbine components. Composite materials, particularly carbon fiber reinforced polymers CFRP and glass fiber reinforced polymers GFRP, emerge as transformative candidates for structural retrofitting. Lightweight panels and seismic dampers in megaprojects. Their extraordinary strength-to-weight ratios and resistance to corrosion motivate incorporation in bridges, high-rise facades, and infrastructure refurbishment. Engineering challenges involve bonding durability, fire resistance, and scaling manufacturing processes to large components. Concrete steel composite systems integrate the compressive capabilities of concrete with tensile steel reinforcement, advanced by innovations such as externally bonded CFRP reinforcements and post-tension tendons enabling prefabricated modular megaproject construction with accelerated schedules and quality control. Smart materials embed sensing and adaptive capabilities within structural components. Piezoelectric sensors installed in concrete or steel elements monitor strain, temperature, and crack propagation, feeding real-time data streams enabling predictive maintenance and extending asset lifespan. Shape memory alloys incorporated in bridge bearings or seismic dampers enable self-centering post-earthquake recovery, reducing repair times and costs. Sustainability imperatives press materials innovation toward reduced carbon footprints. Novel cements utilize clinker substitution by industrial byproducts reducing CO2 emissions. Carbon capture and utilization incorporated into cement production signify groundbreaking steps. Recycling and reuse strategies transform demolition waste into aggregate substitutes. Bio-based polymers and green composites explore renewable feedstocks, minimizing environmental impact. Additive manufacturing, or 3D printing, disrupts conventional materials processing, allowing fabrication of complex, optimized components with tailored properties and reduced waste. Pilot megaprojects use additive techniques for bridge components, architectural elements, and mechanical parts with performance verified through rigorous structural testing. Fire-resistant materials and coatings incorporating intumescent layers, ceramics, and mineral additives protect structures in megaprojects demanding heightened safety standards, especially in high-rise buildings and tunnels. Thermal barrier technologies evolve to resist heat fluxes in extreme environments, including aerospace applications. Nanomaterial research pushes frontiers with graphene-enhanced concretes and coatings, offering enhanced conductivity, mechanical performance, and self-healing capabilities. These innovations anticipate structures capable of autonomously responding to damage, environmental stimuli, or load changes. Integration of these advanced materials into megaprojects demands multidisciplinary collaboration, spanning materials science, structural engineering, chemistry, and manufacturing disciplines. Long-term performance validation through accelerated aging tests and field monitoring ensures reliability under real-world conditions. Challenges remain in scaling laboratory breakthroughs to economically feasible, large-scale production compatible with stringent quality assurance and regulatory frameworks. Ultimately, materials innovation catalyzes the leap from conceptual megaproject visions to tangible, enduring infrastructures capable of serving society's evolving demands securely, sustainably, and beautifully. Logistics and construction management constitute the vital circulatory system fueling megaprojects, orchestrating countless moving parts, materials, equipment, human resources, toward a singular engineered vision. The staggering scale and intricate interdependencies in megaprojects elevate logistical challenges into core determinants of success, demanding innovative management, technology integration, and adaptive strategies capable of navigating uncertainty, complexity, and scale. At the outset, supply chain orchestration in megaprojects involves sourcing enormous quantities of materials, steel, concrete, aggregates, specialty components from geographically dispersed suppliers. This necessitates meticulous procurement planning, balancing cost, quality, delivery reliability, and geopolitical factors. Supply chain disruptions from raw material shortages, transportation strikes, equipment breakdowns to political embargoes pose significant risks, potentially cascading into schedule delays and cost overruns. Agile supply management integrates diversified supplier bases, inventory buffers, and just-in-time principles tailored to mega-project scale. Digital procurement platforms employing blockchain-enhanced transparency, traceability, and contract enforcement, mitigating fraud and ensuring compliance. Transportation logistics manage the flow of massive and often oversized components, from bridge sections and turbine blades to precast concrete segments, requiring multimodal routes combining maritime, rail, road, and air freight. Engineering logistics include specialized equipment such as heavy lift cranes, self-propelled modular transporters, SPMTs, and floating shear leg cranes capable of positioning components within millimeter precision under arduous conditions. Route surveys assess load-bearing capacities, bridge clearances, and turning radii to enable safe, efficient movement. Construction site staging areas serve as temporary retreats for storage, pre-assembly, and quality checks, integral for seamless workflow. Workforce management in megaprojects involves aligning thousands of laborers, engineers, supervisors, and specialists, often representing diverse cultural, linguistic, and professional backgrounds. Effective coordination mandates integrated workforce scheduling software, optimizing shift rotations, skill matching, and training requirements in compliance with safety and labor regulations. Multi-level communication platforms facilitate real-time issue reporting, knowledge sharing, and rapid decision-making, linking field crews with office-based planners. Comprehensive health, safety, and environmental HSE programs utilize behavioral safety training, incident analytics, and hazard identification protocols, reducing accident rates in high-risk environments. Construction sequencing, a pivotal planning element, synchronizes activities, ensuring structural stability and resource availability. Critical path analysis (CPA) and program evaluation review techniques, combined with 4D BIM models, enable visualization of temporal spatial interactions, anticipating congestion, clashes, and resource conflicts. Modular construction techniques, employing prefabricated building units, accelerate schedules and enhance quality control, necessitating precise tolerance management and logistic synchronization. Adaptive project controls incorporate earned value management (EVM), integrating scope, schedule, and cost metrics, facilitating early detection of deviations and corrective actions. Risk management frameworks encompass probabilistic modeling, quantifying uncertainties from geological surprises to weather impacts, supporting contingency allocation and scenario planning. Decision support systems powered by AI analyze vast data sets to forecast impacts and optimize resource deployment dynamically. Quality assurance and control (QA/QC) span material certifications, on-site inspections, and non-destructive testing methods including ultrasonic, radiographic, and thermographic techniques, ensuring compliance with standards and design specifications. Digital documentation systems preserve audit trails vital for regulatory approval and future maintenance. Environmental management integrates monitoring of air quality, noise, water quality, and biodiversity impacts with real-time data acquisition, feeding adaptive mitigation measures such as dust suppression, noise barriers, and water treatment. Permitting and community engagement maintain social license to operate, addressing grievances proactively and fostering inclusive participation. Technological advancements transform logistics and management. IoT sensors track equipment location, usage, and condition, enabling predictive maintenance, reducing downtime. Wearable devices monitor worker vitals and environmental exposures, enhancing safety oversight. Autonomous vehicles and drones undertake materials transport and site inspection tasks, augmenting human capacities and reducing risks. Virtual and augmented reality platforms support training and remote guidance, reducing errors and improving productivity. Megaprojects impose extended timelines, often spanning a decade or more, making knowledge management critical. Systems capturing accumulated lessons learned, evolving best practices, and operational insights guard against repetition of past mistakes and promote continuous improvement. Financial management integrates cash flow forecasting, milestone payments, and risk-adjusted budgeting underpinning stakeholder confidence. Contractual frameworks embrace integrated project delivery, IPD, design build operate, DBO, and public-private partnerships, PPP, aligning incentives and responsibilities. In essence, logistics and construction management for megaprojects transcend routine scheduling and planning. They embody complex systemic orchestration of resources, risks, people, and technology, harmonizing fragmented elements into monumental success. This vital domain ensures megaprojects advance from grandiose blueprints to tangible realities capable of serving generations. Risk management, insurance strategies, and safety engineering constitute indispensable pillars, supporting the colossal scales and complexities of megaprojects. In arenas where cost overruns can reach billions, schedules span decades, and human lives hang in delicate balance, meticulous anticipation, mitigation, and control of risk become fundamental not only to project success, but to societal trust. This comprehensive exploration unpacks the mechanisms, methodologies, and innovations safeguarding megaprojects against uncertainties inherent in their scale and scope. At the foundation lies risk identification and assessment, a rigorous multidimensional process mapping potential threats spanning technical, financial, environmental, political, and operational domains. Technical risks encompass unforeseen geological formations disrupting tunneling, material supply delays, design errors, and construction accidents. Financial risks incorporate cost escalations due to raw material volatility, labor disputes, or currency fluctuations. Environmental risks extend to habitat degradation, pollution events, or climatic extremes jeopardizing schedule and permitting. Political and regulatory risks emerge from policy shifts, community opposition, or legal challenges impacting approvals and stakeholder engagement. Sophisticated qualitative and quantitative risk analysis techniques quantify likelihoods and impacts to prioritize mitigation. Monte Carlo simulations model cost and schedule uncertainties, producing probabilistic forecasts under varying assumptions. Failure mode and effects analysis (FMEA) systematically explores component-level failure pathways and their system's so-called downstream effects. Decision trees map conditional risk evolution, enabling dynamic risk response planning. Root cause analyses of prior megaproject failures provide empirical insights guiding proactive hazard identification. Risk treatment strategies bifurcate into avoidance, reduction, transfer, and acceptance. Avoidance involves altering designs or scopes to eliminate high-risk elements such as substituting fragile materials or rerouting alignments away from unstable geology. Reduction measures embed redundancies, quality controls, and enhance surveillance, minimizing occurrence and consequence severity. Transferring risks to insurers and contractors redistributes burdens through contractual mechanisms, fixed-price contracts, performance bonds, and indemnity clauses, linking incentives and responsibilities. Residual risks accepted are continuously monitored with contingency reserves. Insurance underwriting for megaprojects differs fundamentally from standard policies, necessitating bespoke coverages reflecting project-specific perils. Engineering and construction all-risk CAR policies provide broad protection against physical damage during construction phases. Delay in startup DSU insurance mitigates income losses arising from construction or commissioning delays. Third-party liability policies safeguard against environmental or property damage claims. Insurers insist on rigorous risk management frameworks, conducting ongoing engineering assessments and site inspections before underwriting exposures. Safety engineering in megaprojects integrates multiple dimensions. Occupational safety and health OSH programs encompass hazard identification, risk mitigation protocols, worker training, incident reporting, and emergency preparedness tailored to complex, evolving site conditions involving hundreds or thousands of personnel. Implementation of behavioral safety programs fosters proactive risk awareness. Advanced wearable technologies monitor worker health indicators and environmental exposures real time, enabling early intervention and reducing accidents. Process safety engineering applies to chemical, nuclear, and energy megaprojects where catastrophic failures can have widespread consequences. Layers of protection analysis, LOPA, identify safeguards and conditional probabilities of hazardous event occurrences. Safety instrumented systems, SIS, employing redundant sensors, logic solvers, and actuators, automatically trigger mitigations, such as shutdowns or ventilation. Continuous safety audits and incident investigations, feed improvement cycles. Structural safety involves designing for ultimate limit states including overload, fatigue, impact, and natural hazards. Performance-based codes tailor safety factors to project specific risk profiles. Real-time structural health monitoring systems employing fiber optics, accelerometers, and strain gauges provide early warnings of deterioration or damage. Project governance incorporates integrated risk management committees, consolidating technical, financial, legal, safety, and public relations perspectives. Fostering holistic decision-making. Predictive analytics and AI tools increasingly augment risk identification and scenario planning, improving responsiveness and adaptation to emergent conditions. Crisis management frameworks establish rapid communication channels, predefined roles and response templates enabling coordinated action during accidents or natural disasters, minimizing casualties and damage. Exercises and simulations validate preparedness. Risk culture cultivation is pivotal, embedding safety and risk consciousness at all organizational levels, promoting transparency, accountability, and continuous learning. Lessons learned, databases benchmark performance and disseminate knowledge across projects and industries. Regulatory compliance requires adherence to international and local standards spanning environmental protection, worker safety, construction quality, and post-construction monitoring, enforced by authorities with inspection and certification powers. Financial risk transfer mechanisms evolve with innovative instruments such as parametric insurance, catastrophe bonds, and public-private partnership risk-sharing agreements, providing tailored capital solutions aligned with project life cycles. Ethical dimensions underscore risk management, emphasizing community rights, environmental justice, and equitable sharing of benefits and burdens, integrating stakeholder participation and grievance mechanisms. In summary, risk management, insurance, and safety engineering synthesize scientific rigor, technological innovation, organizational discipline, and ethical commitment to secure the viability, safety, and societal acceptance of megaprojects. Their effective integration distinguishes enduring engineering legacies from transitory ventures. Financing, procurement, and contractual frameworks reside at the financial and legal center of megaproject success, composing an intricate architecture that underwrites enormous capital commitments, governs multi-stakeholder relationships, and balances risks and rewards. These foundational systems translate grand engineering visions into executable realities, navigating economic complexity, regulatory landscapes, and evolving market dynamics. The sheer scale of megaproject investments, ranging from billions to tens of billions of dollars, necessitates diversified and innovative financing structures. Traditional public funding often blends with private capital through public-private partnerships, HPPs, joint ventures, and multilateral development bank loans. Finanzierungsmodelle distribute costs and risks appropriately among governments, investors, lenders, and contractors, aligning interests for the long-term performance and socioeconomic returns of critical infrastructure. Investment appraisal incorporates rigorous financial modeling, including net present value, NPV, internal rate of return, IRR, and sensitivity analyses, evaluating project viability under various economic scenarios and risk conditions. Scenario-based stress tests assess resilience against currency fluctuations, interest rate variations, demand uncertainties, and potential delays. Economic impact assessments quantify broader societal benefits, augmenting conventional financial metrics, informing public sector decisions on subsidies or guarantees. Procurement strategies select contractors and suppliers capable of delivering megaproject components efficiently, safely, and to standard. Approaches vary from traditional design, bid, build to integrated design, build, operate (DBO). Each method transfers varying degrees of design responsibility and risk to contractors. Competitive bidding processes enforce transparency and efficiency, yet megaprojects often require early contractor involvement and collaborative agreements to manage complexity and innovation. Contractual frameworks constitute the keystone aligning obligations, incentives, and liabilities. Large megaproject contracts incorporate detailed scopes, performance benchmarks, milestones, and penalty clauses ensuring accountability. Collaboration enhancing contracts, such as alliance contracting, promote shared risk and aligned goals, fostering flexibility and problem solving. Risk allocation models assign responsibilities for design errors, unforeseen ground conditions, supply chain disruptions, and force majeure events thoughtfully to prevent disputes and maintain project momentum. Payment mechanisms link deliverables to progress using milestone payments, cost reimbursable provisions with guaranteed maximum prices, or lump sum agreements, calibrated for appropriate incentive structures. Financial penalties and bonuses motivate adherence to schedule, budget, quality, and safety targets. Claims management systems address disputes effectively through dispute resolution boards, mediation, and arbitration, minimizing litigation risks. Legal compliance integrates construction laws, environmental regulations, labor standards, intellectual property rights, and international investment treaties, requiring contracts and financing documents to embed relevant provisions safeguarding all parties. Governance arrangements overseeing megaprojects establish steering committees, independent auditors, and monitoring agencies, ensuring fiduciary responsibility, transparency, and ethical conduct. Stakeholder engagement strategies integrate community consultation and grievance mechanisms, embedding social license to operate into contractual commitments. Financial risk mitigation utilizes portfolio diversification. Insurance instruments including political risk insurance and contractual indemnities protecting against exogenous shocks. Multilateral financial institutions often facilitate credit enhancement or co-financing, improving access to favorable capital. Innovations in green bonds and sustainability-linked loans align financing with environmental and social governance (ESG) criteria, reflecting investor and public expectations for responsible infrastructure development. Procurement digitization leverages e-tendering, blockchain-based contract administration, and real-time performance dashboards, enhancing transparency, efficiency, and compliance monitoring. Multi-jurisdictional megaprojects navigate complex tax, labor, and customs regimes requiring harmonized contractual language and robust legal expertise to manage cross-border challenges. Effective integration of financing, procurement, and contracting mechanisms is pivotal to megaproject delivery, mitigating financial exposure, optimizing resource allocation, sustaining collaborative relationships, and adapting dynamically to evolving project complexities. This intricate financial and legal scaffolding empowers engineers and stakeholders to translate visionary mega infrastructure into enduring societal benefits supported by sound economic stewardship. Social and environmental impact management within megaprojects emerges as a critical and intricate dimension, shaping not only engineering outcomes but also the legitimacy, sustainability, and acceptance of these massive undertakings. The scale and influence of megaprojects inevitably reconfigure landscapes, ecosystems, and communities, necessitating holistic frameworks that anticipate, assess, mitigate, and monitor complex social and ecological realities with ethical rigor and scientific precision. At the forefront lies comprehensive impact assessment processes mandated early in project life cycles. Environmental impact assessments (EIA), along with social impact assessments (SIA), provide systematic procedures to analyze probable adverse and beneficial effects, encompassing biodiversity degradation, water quality shifts, air emissions, noise pollution, cultural heritage disturbance, population displacement, and livelihood disruptions. These assessments employ multidisciplinary methodologies: field surveys documenting flora and fauna, hydrological modeling, predicting alterations in water regimes, socioeconomic analyses, characterizing vulnerable populations, and qualitative participatory approaches involving questionnaires, focus groups, and stakeholder interviews. Ecological considerations extend beyond compliance minima, embracing ecosystem services valuation, quantifying benefits such as carbon sequestration, clean water provision, and soil fertility maintained or enhanced by conservation measures embedded within project design. Biodiversity offsets and habitat restoration initiatives aim to compensate for unavoidable impacts, applying landscape-scale planning, integrating corridor design, facilitating species migration, and genetic flow. Protected areas and buffer zones are designated, aided by Geographic Information System (GIS) mapping and remote sensing data monitoring environmental indicator trends. The social fabric surrounding megaprojects merits profound engagement. Resettlement and compensation plans, adhering to principles such as those articulated by the World Bank's Environmental and Social Framework (ESF), strive to restore and improve livelihoods, incorporate culturally sensitive measures, and ensure participation of affected populations. Urban megaprojects confront gentrification risks and housing affordability issues, prompting comprehensive urban planning efforts including social infrastructure provision, public space development, and transit accessibility enhancements. Public consultation permeates decision-making, fostering trust and legitimacy through transparency and dialogue. Communication strategies deploy multi-channel outreach, public hearings, information kiosks, social media platforms, and grievance redress mechanisms, ensuring concerns are documented, addressed, and integrated into adaptive management. Multi-stakeholder forums involving indigenous groups, NGOs, local governments, and private sector representatives nurture collaborative stewardship models. Environmental and social management plans (ESMPs) operationalize mitigation measures through concrete actions, emission reduction technologies, sediment control installations, noise abatement barriers, construction timing adjustments to protect breeding seasons, and occupational health protocols, minimizing dust and chemical exposures among workers and residents. Monitoring programs utilize sensor networks, biological indicators, and community-based reporting systems providing real-time data supporting continuous improvement. Performance indicators encompass not only regulatory compliance, but also qualitative indicators of community well-being and ecological resilience. Climate change introduces emergent dimensions demanding forward-looking risk assessments considering sea level rise, temperature increases, and extreme weather event frequency. Engineering adaptations encompass floodproofing, landscape buffering, and low-impact construction methodologies, contributing to megaprojects' overall climate resilience and carbon neutrality efforts. Ethical considerations emphasize procedural justice, equitable participation in decisions affecting communities, distributive justice, fair allocation of project benefits and burdens, and recognition justice, respect for cultural identities and traditional knowledge systems. These principles challenge engineering pragmatism to embrace human rights, cultural heritage protection, and intergenerational equity. Cumulative impact assessments analyze how multiple megaprojects and development activities interact spatially and temporally, recognizing compounded pressures on ecosystems and societies, requiring coordinated regional planning and policy coherence. Legal and regulatory frameworks provide minimum standards, but emerging best practices emphasize voluntary corporate social responsibility (CSR) commitments, aligning with United Nations Sustainable Development Goals (SDGs) and international standards such as ISO 14001 for environmental management and ISO 26000 for social responsibility. Adaptive management frameworks institutionalize learning and flexibility, enabling megaproject governance to respond dynamically to unforeseen impacts, or shifting baselines informed by monitoring and stakeholder feedback. Economic valuation of social and environmental impacts informs cost-benefit analyses, reflecting true project value, extending beyond financial returns, supporting balanced decision-making, aligned with sustainability imperatives. In essence, social and environmental impact management elevates megaproject engineering from technical execution toward integrated stewardship that harmonizes human aspirations and natural systems, laying foundations for enduring legacies that sustain well-being, equity, and ecological integrity. Safety engineering and monitoring in megaprojects represent a vital frontier, transforming how humanity anticipates, controls, and responds to inherent risks within massive construction and operational activities. At these extraordinary scales, ensuring the protection of workers, communities, and assets becomes an intricate synergy of cutting-edge detection technologies, predictive analytics, resilient designs, and organizational culture fostering continuous vigilance. This exploration unpacks the sophisticated methodologies and innovative tools safeguarding megaprojects amidst complexity and uncertainty. At the core, health and safety management systems integrate systematic hazard identification and risk assessment processes, encompassing physical, chemical, biological, ergonomic, and psychosocial risks. The development of comprehensive risk registers catalogs hazards ranging from heavy equipment operation, working at heights, confined space entry, to exposure to vibration and noise. Hierarchies of control, from elimination through substitution, engineering controls, administrative measures to personal protective equipment, PPE, form the structured basis for preventive actions. Technological evolution propels safety monitoring beyond traditional manual inspections. Internet of Things IoT devices, embedded throughout work sites, measure environmental parameters like air quality, temperature, and particulate levels, alerting to hazardous conditions instantaneously. Wearable technologies monitor biometric data, such as heart rate, fatigue indicators, and physical strain, enabling real-time intervention to prevent accidents or health events. Geofencing technologies restrict access to dangerous zones and trace personnel location, enhancing emergency responsiveness. Structural safety monitoring leverages embedded fiber optic sensors and strain gauges distributed within foundations, beams, and concrete segments, detecting stress variations, cracks, and deformations. These systems transmit continuous real-time data streamed into central monitoring facilities, where machine learning algorithms differentiate normal operational fluctuations from critical anomalies. Early warning systems enable preemptive maintenance, reducing the likelihood of catastrophic failures in bridges, dams, and high-rise buildings. Unmanned aerial vehicles, drones equipped with high-resolution cameras, thermal imaging, and LiDAR perform aerial inspections of challenging or hazardous environments, increasing inspection frequency and detail while minimizing human risk exposure. Data processing pipelines apply image recognition and defect detection algorithms, automating condition assessment and flagging areas requiring human attention. Safety-critical software, embedded in construction machinery and process control systems, enforces operational limits, preventing hazardous actions through interlocks and automatic shutdowns. Advanced robotics undertake perilous tasks such as demolition, deep excavation, or nuclear waste handling, removing personnel from harm. Emergency preparedness plans integrate comprehensive scenario analyses encompassing fires, explosions, chemical spills, natural disasters, and structural failures. Simulated drills and virtual reality-based training immerse workers and management in realistic hazard situations, developing response competencies under controlled conditions. Incident command systems coordinate multidisciplinary responses, ensuring rapid, coordinated, and effective action, minimizing impacts. Regulatory compliance frameworks mandate certification and regular audits, verifying adherence to health, safety, and environmental legislation globally. International standards. ISO 45001 for occupational health and safety management systems and OHS AS 1801 guide comprehensive program development and continuous improvement cycles. Organizational safety culture remains paramount. It entails leadership commitment, worker empowerment, transparent communication channels, and shared accountability, fostering proactive hazard identification and reporting without fear of reprisal. Data-driven performance metrics monitor safety leadership effectiveness and workforce engagement. Risk communication strategies transparently disseminate information to workers, contractors, and surrounding communities, enhancing awareness and preparedness. Collaborative forums engage all stakeholders addressing concerns and co-creating safer workplaces. Psychosocial health initiatives address mental well-being, managing stressors intrinsic to mega-project environments, including shift patterns, high pressure, and isolation. Programs support resilience through counseling, peer networks, and workload management. Financial impacts of safety improvements reflect reduced accident-related costs, insurance premiums, and project delays, reinforcing business cases for sustained investment. Emerging research explores predictive analytics, leveraging big data, integrating weather forecasts, equipment usage, and human factors, seeking to anticipate accident precursors, enabling proactive interventions. In conclusion, safety engineering and monitoring within megaprojects exemplify humanity's commitment to protect life and assets through technological innovation, rigorous management, and cultural transformation. As megaproject scales and complexities advance unabated, evolving safety paradigms remain essential guardians converting ambition into achievement without compromise. Please confirm readiness for Part 17, which will explore the nexus of environmental sustainability and innovation driving future megaproject development, composed with equal comprehensive scope and originality. Part 16, Safety engineering and monitoring in megaprojects constitute a complex nexus of technology, process, and culture, designed to anticipate and mitigate the multifaceted risks inherent in colossal infrastructural undertakings. At these immense scales, where thousands of workers, intricate machinery, and volatile materials converge within vast construction sites or operational environments, the imperative to protect human life, environmental integrity, and asset longevity demands innovation, precision, and relentless vigilance. Central to modern safety engineering are integrated health and safety management systems, incorporating proactive, systematic identification of hazards spanning physical, chemical, ergonomic, and psychosocial domains. These systems leverage risk registers, cataloging potential incident causes, ranging from heavy equipment operation and working at heights to exposure to noise and fatigue, serving as foundations upon which tailored mitigation hierarchies unfold. Prioritizing elimination, engineering controls, administrative measures, and personal protective equipment, PPE. Technological advancements exponentially enhance monitoring capabilities. IoT devices embedded throughout projects collect real-time environmental data on air quality, temperature, vibration, and hazardous gas concentrations, generating immediate alerts when thresholds are exceeded. Wearable technology monitors biometric parameters such as heart rate variability and physical strain, providing early warning of fatigue or health stress, augmenting human judgment with data-driven insights. Geofencing restricts access to hazardous zones, tracking personnel movement for emergency readiness. Structural health monitoring amalgamates fiber optic sensors, strain gauges, and accelerometers embedded within foundations, load-bearing members, and precast segments. These instruments transmit continuous data feeds analyzed by AI-enhanced platforms distinguishing normal operational variances from signs of fatigue, corrosion, or cracking, enabling condition-based maintenance that preempts failures. Unmanned aerial systems, drones equipped with multispectral cameras, thermal imaging, and LiDAR conduct frequent high-fidelity inspections of inaccessible or dangerous regions, bridge cables, dam faces, or tall structures, minimizing personnel risk and expediting defect identification. Automated image analysis workflows further accelerate assessment and intervention prioritization. Safety-critical embedded software governs operational parameters of heavy machinery, process systems, and automated workflows, activating interlocks and emergency shutdowns to prevent unsafe conditions. Robotics and autonomous equipment undertake hazardous or repetitive tasks. High-altitude welding, deep excavation, confined space cleaning, reducing human exposure. Comprehensive emergency preparedness involves scenario-based planning for fires, chemical releases, natural disasters, and structural collapses. Virtual reality simulations immerse workers and decision-makers in realistic crisis environments, fostering rapid, coordinated response readiness. Incident command systems ensure structured multi-agency interaction, optimizing resources and minimizing harm during events. Regulatory compliance is enforced through certification audits aligned with ISO 45001 and equivalent regional standards, anchoring continuous improvement cycles grounded in empirical performance data. Organizations cultivate safety cultures emphasizing transparent communication, shared accountability, worker empowerment, and proactive hazard identification. Risk communication employs clear messaging, multi-channel dissemination, and inclusion of frontline workers and communities, bolstering awareness and trust. Psychosocial well-being programs address mental health challenges intrinsic to mega-project pressures via counseling, peer support, and workload management. Financial analyses underscore safety investments returns by reducing accident-related costs, insurance premiums, and unplanned delays, validating resource allocation for preventative strategies. Emerging research explores predictive safety analytics, integrating operational metrics, environmental data, and human factors aiming to forecast accident precursors with machine learning, enabling preemptive interventions and adaptive controls. In sum, megaproject safety engineering and monitoring evolve as dynamic, technology-enabled ecosystems, synthesizing scientific, managerial, and humanistic strengths. Their vigilant stewardship assures that engineering horizons expand responsibly, safeguarding lives and ecosystems while delivering transformative infrastructure. Environmental sustainability has emerged as an imperative driver, reshaping the conception, execution, and operation of megaprojects, fundamentally altering engineering paradigms from merely technical constructs into integrated ecosystems, balancing human needs with planetary stewardship. As global consciousness heightens around climate change, resource depletion, and biodiversity loss, megaprojects face escalating mandates to embed sustainability principles holistically, applying innovative strategies across the entire project lifecycle. From inception, sustainable megaproject design prioritizes site selection, minimizing ecological footprints while optimizing connectivity and resource utilization. Landscape architecture harmonizes native vegetation with engineered earthworks, creating multifunctional green spaces, providing habitat corridors, air purification, and thermal regulation. Sustainable drainage systems utilize permeable pavements, bioswales, and retention basins, mitigating flood risks and improving water quality through natural filtration processes, reducing reliance on traditional piped infrastructure. Material stewardship guides procurement towards low-carbon and recycled content materials, certified by independent standards such as the Cradle-to-Cradle Framework or Leadership in Energy and Environmental Design, LEED. Engineers prioritize alternatives to high-embodied carbon materials, incorporating supplementary cementitious materials to reduce clinker usage in concrete or employing timber composites responsibly sourced supporting carbon sequestration. Modular construction methods reduce waste and enhance deconstruction potential, enabling circular economy practices at megaproject scale. Energy efficiency is embedded through integration of passive design features. Maximize daylighting, natural ventilation, and thermal mass to reduce heating, cooling, and lighting loads. Renewable energy systems, including photovoltaic arrays, wind turbines, geothermal heat pumps, and biomass cogeneration, are integrated with smart grid management, enabling dynamic load balancing, storage optimization, and peak demand reduction. Building Energy Modeling (BM) software informs iterative design refinements, optimizing energy performance to net zero or net positive targets. Water conservation strategies encompass rainwater harvesting, grey water recycling, and low-flow fixtures, reducing potable water demand. Smart water metering and leak detection systems enhance operational efficiency and resource accountability. Advanced wastewater treatment employing membrane bioreactors facilitates on-site reuse, supporting irrigation and non-potable applications. Biodiversity conservation engages through comprehensive environmental impact statements, guiding avoidance, minimization, and offsetting of habitat disturbances. Collaborations with ecologists develop ecological restoration programs, reintroducing native flora and fauna, post-construction rejuvenating ecosystem services, disrupted during megaproject development, green infrastructure elements, green roofs, living walls, urban wetlands, ameliorate urban heat islands, and strengthen ecological resilience amidst expanding urban footprints. Transportation megaprojects incorporate multimodal accessibility, reducing private vehicle dependence, promoting walking, cycling, and public transit, diminishing greenhouse gas emissions and air pollution. Advanced modeling forecasts travel demand, facilitating transit-oriented development, harmonizing land use with transportation infrastructure. Waste management innovation integrates construction and demolition waste. CDW recycling, the processing and reuse of concrete, metals, and wood within site boundaries or local industries, minimizing landfill contributions. Circular resource flows guide procurement, construction, and operations, fostering sustainable supply chains. Carbon management entails rigorous life cycle assessments, quantifying embodied and operational emissions, steering design and material choices, carbon offsetting projects involving reforestation, soil carbon sequestration, or renewable energy investments, supplement direct reduction efforts, striving for climate neutrality. Social sustainability imbues project frameworks emphasizing equitable access, community empowerment, cultural heritage preservation, and health promotion. Inclusive design methodologies ensure accessibility and functionality, accommodating diverse populations. Stakeholder engagement processes facilitate transparency, participation, and conflict resolution, nurturing social license. Digital technologies amplify sustainability efforts. IoT sensor networks monitor air quality, energy use, and biodiversity indices, enabling responsive management. Data analytics and AI optimize resource allocation and predictive maintenance, minimizing wasteful overuse. Certification and rating systems such as Envision, BREEAM, and WELL provide measurable benchmarks guiding sustainable megaproject delivery, fostering accountability and continuous improvement. Resilience planning addresses increasing climate volatility, incorporating adaptive designs resilient against flood, heat waves, droughts, and storms, ensuring infrastructural longevity and operational continuity. Challenges persist in balancing economic feasibility with environmental ambitions requiring innovative financing mechanisms, such as green bonds, sustainability-linked loans, and public incentive frameworks accelerating adoption. Cross-disciplinary collaboration, spanning engineers, ecologists, economists, sociologists, and policymakers, remains essential, integrating multifaceted sustainability objectives into coherent megaproject strategies. In essence, environmental sustainability catalyzes a profound transformation in megaproject engineering, from linear exploitation towards regenerative design philosophies, harmonizing built and natural environments, securing prosperity within planetary boundaries now and into the future. Workforce development and human factors engineering constitute vital but frequently underappreciated pillars, underpinning the success of megaprojects. The sheer scale, complexity, and diversity of these endeavors demand not only technical excellence, but an astute understanding of human capabilities, ergonomics, training, and organizational culture, harmonized to optimize productivity, safety, well-being, and innovation across vast teams operating under dynamic conditions. Megaproject workforces often encompass tens of thousands of personnel, spanning engineers, skilled tradespersons, laborers, supervisors, specialists, and support staff from diverse cultural, educational, and linguistic backgrounds. Coordinating this human capital requires comprehensive workforce planning, encompassing recruitment strategies, attracting talent lines sustainably, skill gap analyses, guiding targeted training programs, and flexible deployment, optimizing labor allocation amid fluctuating project phases and geographies. Training innovations deploy blended learning techniques, combining classroom instruction, virtual reality VR simulations, augmented reality AR overlays, and gamified modules, enabling immersive skill acquisition, hazard recognition, and procedure rehearsal under realistic scenarios. Such approaches reduce accident rates and increase operational efficiency by reinforcing cognitive retention and muscle memory, critical in hazardous, precision-demanding environments. Human factors engineering integrates ergonomic principles into equipment, workstation, and workflow design, minimizing fatigue, musculoskeletal disorder risks, and cognitive overload. Wearable exoskeletons augment physical capabilities, reducing strain during heavy lifting or repetitive tasks. Tool and machine interfaces evolve, incorporating intuitive controls, haptic feedback, and voice commands, reducing error propensity and increasing responsiveness. Mental health and psychosocial well-being receive elevated attention, recognizing the stressors, extended shift patterns, isolation, high physical demands, common in megaproject environments. Supportive programs encompass counseling, peer networks, workload optimization, and healthy workplace design, fostering resilience, engagement, and retention. Communication systems leverage multilingual platforms, inclusive signage, and culturally sensitive training materials, bridging language and cultural barriers, enhancing clarity and cooperation in multicultural teams. Digital collaboration tools connect dispersed teams, facilitating real-time coordination, reducing misunderstandings, propelling productivity. Leadership development programs cultivate transformational leadership styles, emphasizing empathy, inclusivity, decision accountability, and proactive safety cultures. Leaders equipped to motivate, resolve conflicts, and foster continuous learning create environments where safety and quality thrive. Organizational safety culture represents a foundational determinant of performance. Measuring metrics such as near-miss reporting rates, hazard identification participation, and leadership safety engagement enables continuous culture reinforcement and identification of improvement opportunities. Shift scheduling integrates human circadian rhythms and fatigue science, optimizing alertness and reducing errors. Monitoring worker alertness using physiological measures such as eye tracking or heart rate variability enables dynamic shift adjustments, preventing productivity dips and accidents. Collaborative robots, cobots, enhance human-machine symbiosis, automating repetitive, high-risk tasks while maintaining human oversight and control, boosting efficiency and safety. Wearable sensors monitor physiological parameters for personalized fatigue management interventions. Workforce diversity and inclusion strategies cultivate environments valuing varied perspectives, enhancing innovation, safety, and quality. Accessibility accommodations ensure participation of differently abled individuals, strengthening community integration and talent pools. Knowledge management systems capture tacit expertise, promoting mentoring relationships and safeguarding organizational memory amidst workforce turnover, inherent in extended mega-project timelines. Regulatory frameworks mandate occupational health and safety standards compliance supported by continuous auditing, benchmarking, and worker participation in safety committees, ensuring worker voices inform procedural improvements. Economic considerations demonstrate that robust workforce development and human factors engineering reduce accident-related costs, improve productivity, and enhance morale, creating virtuous cycles supporting mega-project success. In sum, the human dimension represents the irreplaceable engine driving the colossal machinery of mega-projects. Applying scientific ergonomics, dynamic training, and inclusive leadership unlocks human potential, fostering safer, more efficient, and innovative project delivery. International collaboration and governance form essential frameworks, enabling the successful execution of megaprojects that transcend borders, cultures, and legal systems. As these projects frequently involve multinational funding, expertise, and geopolitical considerations, their management demands sophisticated coordination, transparent governance mechanisms, and cultural competence harmonized to align diverse stakeholder interests while ensuring technical excellence and sustainability. Cross-border megaprojects, such as transnational transportation corridors, shared water management infrastructures, or space exploration alliances, entail navigating varied regulatory environments encompassing environmental laws, labor codes, safety standards, and procurement regulations. Harmonization efforts deploy multilateral treaties, memoranda of understanding, and joint governance bodies, establishing unified standards, dispute resolution mechanisms, and compliance monitoring frameworks, mitigating risks from legal inconsistencies or jurisdictional conflicts. Financial collaboration integrates sovereign wealth funds, development banks, private investors, and export credit agencies, each with distinct risk appetites, performance criteria, and governance expectations. Structuring financial instruments spans syndicated loans, project bonds, blended finance, and guarantee schemes designed to de-risk investments and align incentives promoting long-term viability and equitable risk sharing. Technical collaboration leverages global knowledge pools, integrating expertise from diverse cultural and disciplinary backgrounds. Multinational consortia, combining firms specializing in engineering, project management, legal services, environmental consultancy, and technology development, establish cross-cultural teams enhancing innovation and problem-solving capacity. Tools facilitating collaboration include multilingual digital platforms, standardized documentation, and interoperable modeling systems, fostering consistency and transparency. Institutional governance structures embody hierarchical and lateral coordination mechanisms, optimizing decision-making efficiency and accountability. Steering committees comprising representatives from involved countries oversee strategic direction, risk management, and stakeholder engagement. Technical advisory panels provide specialized input on complex engineering challenges, ensuring adherence to best practices and standards. Independent monitoring agencies conduct audit and compliance assessments, ensuring integrity and transparency. Cultural competence enhances collaborative effectiveness by recognizing and bridging differences in communication styles, conflict resolution approaches, and organizational norms. Diversity training, inclusive leadership, and knowledge exchange foster trust and relationship building essential in high-stakes mega-project environments. Risk governance integrates transnational perspectives, anticipating geopolitical volatility, currency fluctuations, and policy shifts influencing project timelines and costs. Adaptive governance models incorporate contingency protocols, enabling responsive adjustments, while safeguarding project continuity. Public engagement spans all participating jurisdictions, incorporating culturally tailored outreach, participatory forums, and grievance redress mechanisms, fostering social license across diverse communities and ensuring benefits equitably distributed. Sustainability governance embeds environmental and social safeguards, aligned with international frameworks such as the Equator Principles, UN Sustainable Development Goals, SDGs, and International Finance Corporation (IFC) performance standards promoting responsible megaproject development, transcending national priorities. Knowledge-sharing platforms developed under international cooperation disseminate lessons learned, technical innovations, and best practices, accelerating capacity building globally. These networks strengthen resilience across future megaprojects, confronted with overlapping challenges. Legal instruments support enforcement of contracts, protection of intellectual property, and resolution of cross-border disputes via arbitration and multilateral legal bodies. Innovations in digital governance leverage blockchain for secure, transparent documentation, real-time monitoring dashboards providing multi-dimensional visibility enhancing stakeholder confidence. Ultimately, international collaboration and governance transform megaprojects into platforms of diplomacy, cultural exchange, and innovation, exemplifying cooperative human endeavor, addressing shared challenges and aspirations. Their success depends on harmonizing complex technical, financial, social, and political systems within frameworks, prioritizing transparency, adaptability, equity, and mutual benefit, laying foundations for enduring global partnership and infrastructure legacies. Emerging technologies such as quantum computing, biotechnology, and artificial intelligence are revolutionizing the landscape of megaproject engineering by introducing unprecedented capabilities and complexities that redefine design, execution, and societal impact. These technologies open transformative avenues, enabling solutions to previously intractable challenges, while simultaneously invoking new multidisciplinary engineering dilemmas and ethical considerations, essential for responsible innovation. Quantum computing promises to exponentially accelerate computational tasks critical for megaproject development, including optimization of complex supply chains, simulation of material behaviors at atomic scales, and real-time processing of massive sensor data networks. Unlike classical bits, quantum bits leverage superposition and entanglement to perform parallel computations, potentially transforming engineering analysis for finite element modeling, fluid dynamics, and structural integrity simulations. Engineering quantum computers for industrial application involves overcoming decoherence, error correction, thermal regulation at near absolute zero, and scalable qubit interconnectivity, challenges that parallel the immense scale and precision demands of megaprojects themselves. Biotechnology integration in megaprojects spans advanced biofabrication of materials, living concrete capable of self-repairing cracks through microbial calcium carbonate precipitation, genetically engineered biomaterials with enhanced durability and adaptability, and biological water purification systems harnessing microbial consortia for pollutant degradation. Such bioengineered solutions offer sustainability leaps, reducing resource consumption and ecological impacts. Implementation requires interdisciplinary engineering, harmonizing microbiology, material science, and structural design to ensure reliability and integrate with existing infrastructure. Artificial intelligence pervades megaproject life cycles through enhancing data-driven decision-making, predictive maintenance, automated quality control, and adaptive operational management. Machine learning algorithms mine large data sets, detecting emerging hazard patterns, optimizing resource allocation, and forecasting demand fluctuations. AI-powered robotics execute high-precision fabrication and inspection tasks in hazardous or inaccessible environments, accelerating construction timelines while reducing human risk exposure. Advances in explainable AI ensure transparency and trustworthiness of automated decisions, critical for safety and regulatory compliance. Converging these technologies necessitates robust systems engineering, integrating quantum processors, biohybrid sensors, AI analytics, and traditional infrastructure into coherent, interoperable architectures capable of scalable deployment. Cyber-physical systems embody these integrations, requiring cybersecurity protocols defending against novel threats intrinsic to quantum cryptography, bioinformatic data, and AI autonomy. Societal implications encompass employment transformations as automation reshapes workforce demands, requiring reskilling and social infrastructure adaptation. Ethical frameworks govern deployment considering privacy, equity, environmental justice, and long-term sustainability. Legislation lags technological evolution, necessitating proactive governance models balancing innovation, encouragement, and risk mitigation. Education and training paradigms adapt incorporating interdisciplinary curricula, combining quantum science, synthetic biology, AI engineering, and ethics, preparing future engineers capable of navigating this complex technological horizon. Investment in research infrastructure, cross-sector partnerships, and international cooperation accelerate maturation from laboratory innovation to megaproject applicability, ensuring technological advances translate into tangible societal benefits. In sum, emerging technologies expand the megaproject engineering frontier, beyond physical scale, into realms of quantum precision, living materials, and intelligent autonomy, heralding a paradigm shift integrating computation, biology, and cognition within infrastructure evolution. This fusion promises not only to transform megaproject efficiency, resilience, and sustainability, but also to redefine humanity's interaction with engineered environments, forging pathways toward an adaptive, responsive infrastructure era, intimately woven with life and intelligence. Megaprojects tackling global challenges such as climate adaptation, disaster resilience, and sustainable urbanization represent a critical nexus where engineering innovation, policy foresight, and societal needs converge to safeguard the future of communities worldwide. The escalating frequency and intensity of extreme weather events, rising sea levels, urban population growth, and resource constraints propel megaprojects into new realms of complexity and urgency, demanding multidisciplinary approaches integrating advanced science, robust infrastructure, and social inclusivity. Climate adaptation megaprojects focus on mitigating impacts from sea level rise, temperature fluctuations, and changing precipitation patterns. Coastal defense systems, massive seawalls, dike networks, and storm surge barriers such as the Thames Barrier in London or the Netherlands Maasvlakering are engineered incorporating dynamic hydrodynamic modeling, predicting evolving flood scenarios. These structures employ flexible designs integrating movable gates, sensor arrays measuring water pressure and velocities, and automation systems enabling rapid closure during storm events. Natural infrastructure elements like restored wetlands and mangrove forests complement hard infrastructure buffering wave energy and enhancing biodiversity. Urban megaprojects embed green infrastructure, spreading permeable pavements, green roofs, urban forests, and bioswales, reducing heat islands, managing stormwater runoff, and improving air quality within dense cityscapes. These systems require precise hydraulic engineering, managing overflow rates, pollutant load attenuation, and groundwater recharge aligned with urban growth patterns. IoT-enabled sensor networks provide real-time environmental monitoring, feeding adaptive management platforms, optimizing resource usage. Disaster resilience megaprojects extend beyond physical defenses, incorporating early warning systems deploying satellite remote sensing, seismic sensors, and meteorological data integrated through AI-based predictive analytics, informing evacuation procedures, resource allocation, and infrastructure reinforcement prioritization. Critical facilities and lifelines, hospitals, power stations, transportation networks, are reinforced through resilient structural designs anticipating seismic, flood, or wind load extremes, employing energy dissipation mechanisms, base isolation, redundancy, and modularity, enabling rapid repair and functionality restoration post-disaster. Sustainable urbanization megaprojects integrate high-density mixed-use developments with efficient public transit networks decreasing per capita carbon footprints and enhancing social equity. Smart city grids coordinate decentralized renewable energy generation, storage solutions, and demand response technologies, ensuring grid stability amidst variable energy inputs and consumption patterns. Building design evolves embracing passive solar strategies, low-carbon materials, and circular economy principles, minimizing life cycle environmental impacts. Water management megaprojects address emerging stresses on freshwater availability, exacerbated by climate impacts and urban demands. Large-scale desalination, wastewater recycling plants integrating advanced membrane bioreactors and stormwater capture systems supply resilient water sources. Integrated river basin management coordinates upstream conservation with downstream usage optimizing sustainability. Social resilience remains paramount. Mega-project designs incorporate community engagement to identify vulnerabilities and tailor solutions, ensuring accessibility, affordability, and cultural appropriateness. Disaster displacement mitigation strategies provide inclusive shelter and livelihood recovery infrastructure. International frameworks such as the Sendai Framework for Disaster Risk Reduction and Paris Climate Agreement Guide. Alignment of mega-project objectives with global sustainability goals, enhancing funding access, knowledge sharing, and regulatory compliance. Financial innovation involves climate-adaptive bonds, catastrophe funds, and blended finance, encouraging investment mobilization while managing emerging environmental risk profiles. Megaproject governance embraces adaptive management, incorporating continuous learning, stakeholder feedback, and technological integration, ensuring responsiveness to evolving climatic and social conditions. Technological frontiers leverage digital twins, simulating climate impact scenarios, informing infrastructure adaptation, blockchain securing transparent resource tracking, and AI optimizing resource efficiency and hazard prediction. Challenges entail balancing immediate infrastructure needs with long-term sustainability, addressing uncertainties inherent in climate projections, and ensuring equitable benefit distribution across socioeconomic strata. In conclusion, megaprojects addressing climate adaptation, disaster resilience, and sustainable urbanization epitomize engineering's evolving role, transforming colossal challenges into opportunities for innovative, inclusive, and forward-looking infrastructure capable of safeguarding humanity's shared future. The future of megaproject engineering unfolds at the confluence of emergent technologies, evolving ethical imperatives, and transformative societal needs, sketching a visionary trajectory where human ambition harmonizes with planetary stewardship and equitable progress. This final chapter synthesizes multifaceted insights gleaned from preceding explorations, outlining a roadmap where next-generation megaprojects embody resilience, innovation, inclusivity, and profound responsibility. Technological frontiers propel mega-project capabilities beyond traditional domains, fusing quantum computing's unparalleled simulation power, AI-driven autonomous systems, bioengineered materials, and pervasive digital interconnectivity into cohesive architectures. These tools empower unprecedented optimization of design, construction, operations, and adaptive maintenance, making infrastructure anticipatory and self-healing. Advanced robotics perform hazardous tasks remotely with agility and precision, while sensor-laden environments deliver real-time health insights informing life cycle decisions. Distributed ledger technologies like blockchain secure transparent, immutable construction logs and contractual compliance, fostering trust across multi-stakeholder ecosystems. Ethical frameworks evolve alongside capability, emphasizing precautionary principles, enhanced transparency, and participative governance, ensuring megaproject benefits transcend economic metrics to encompass social justice, cultural preservation, and intergenerational equity. Engineers adopt foresight methodologies, embedding moral deliberation into design choices, risk assessments, and impact mitigation plans. Human rights considerations guide resettlement, labor practices, and community engagement. Equitable access to infrastructure and technology lifts marginalized demographics rather than exacerbating divides. Climate crisis and biodiversity loss catalyze transformation from exploitative to restorative megaproject paradigms. Circular economy design principles govern resource cycles. Materials are sourced sustainably, used efficiently, and reintegrated post-use, minimizing waste and emissions. Ecosystem services are valued integrally, with megaprojects functioning as catalysts for habitat restoration, carbon sequestration, and pollution remediation. Resilience to dynamic environmental stressors becomes non-negotiable, embracing adaptive infrastructures responsive to changing climates, demographics, and technologies. Global collaboration intensifies, transcending nationalistic approaches toward shared infrastructure assets, addressing transboundary challenges such as freshwater scarcity, energy transitions, and disaster risk management. International institutions facilitate harmonized standards, equitable financing, and conflict resolution underpinning large-scale cooperative ventures. Open data initiatives and distributed innovation platforms democratize knowledge, enabling emerging economies to leapfrog and participate fully. Human-centric design assumes primacy, prioritizing accessibility, safety, and comfort, anchoring infrastructures within their cultural, social, and spatial narratives. Inclusiveness permeates all life cycle stages from planning through construction and operation, acknowledging diverse stakeholder values and fostering collective ownership. Education, training, and workforce evolution adapt dynamically to new technological and ethical landscapes, preparing professionals possessing hybrid technical and socio-ecological competencies necessary for complex system stewardship. Financial innovation integrates sustainability-linked bonds, impact investments, and green financing, tailoring flow incentives toward regenerative megaprojects capable of generating positive externalities alongside economic viability. In essence, the future megaproject represents a nexus where engineering transcends bricks and bytes, becoming an instrument for holistic transformation that reconciles human aspiration with earthly limits and social equity. This epoch demands courageous visionaries who navigate complexity with wisdom, rigor, and empathy, crafting megaprojects not solely as infrastructure, but as enduring legacies nurturing thriving communities and resilient biospheres. Our journey through the colossal, the complex, and the cutting edge reveals a profound truth: that engineering's greatest achievement lies not merely in what is constructed, but in how it elevates human potential, aligned with the flourishing of all life on Earth.